Okay. This is John Allison from Market Science. We are going to post the solution to the released FRQ number 5 from the Calculus BC exam for 2025. And we have not looked at the problem yet. Remember, I like to do this cold, where I have not seen the problem, try to emulate or simulate feeling the kids get when they take the test. So here we go. Let's open this problem and look at it. Number 5, I don't post the problem on here, show you the problem on here, so I do post the link to the problem on the College Board website so that you can access it and follow along. But we don't want to violate their copyright restrictions. Okay, so here we go. We have number 5, let f of x be the particular solution to the differential equation. Differential equation dy dx equals 3 minus x times y squared. And has initial condition f of 1 equals -1. We're asked to find f double prime of 1. So y equals f of x. dy dx is going to be f prime. And so we're going to find f double prime of x equals c squared y dx squared. And that's going to be 3 minus x times the derivative of y squared, which is going to be 2 times y times dy dx times 3 minus x plus y squared times the derivative of 3 minus x, which is -1. That's y in terms of x. So we don't have not vectors or parametric or anything like that yet. So negative y squared. So that equals 2y times 3 minus x dy dx minus y squared. Just find that value at the point 1, -1. So we need to evaluate dy dx at the point 1, -1. And that's going to be 3 minus 1 times -1 squared, which is just going to be 2. And so this one we have x equals 1, so d squared y x squared, second derivative of y is going to equal 2 times -1 times 3 minus 1 times 2 dy dx minus, and this is evaluated at the point 1, -1 also, minus y squared, which is -1 squared. We can leave it like that. We don't have to simplify and take a chance on messing up any signs or anything like that. So we're going to leave it like that. That's going to be part A. B says write the second degree Taylor polynomial for f about x equals 1. So remember that f of x equals, we're doing f of 1 plus f prime of 1 times x minus 1 over 1 factorial, which is 1, plus f double prime of 1 times x minus 1 squared over 2 factorial. That will give us a second degree Taylor polynomial about x equals 1. Make sure that y'all can see that on there. Yeah, we got that. Okay, so we know what f of 1 is. F of 1 is -1. And f prime of 1, that's going to be dy dx at 1. I think we evaluated that, did we not? We did, because it had a 1.1 -1. That was 2. So this is going to be plus 2 times x minus 1. And f double prime of 1. That's dy dx squared the second derivative, evaluated at 1, -1. We do have to simplify that, it looks like. So I'm going to go ahead and simplify it over here and put that's going to be 2 times -1 times 2 times 2 minus 1. This is going to be -8 minus 1 equals -9. So I did all that right. So that's going to be -9 times x minus 1 squared over 2. I'm going to double check that derivative, second derivative, just in case. So we're taking the derivative of this, and we got 3 minus x times 2y dy dx. And then we're taking the derivative of this, which is -1 times this, which is 1 squared, so that should be right. 2y, 3y minus x times dy dx minus y squared. And we plugged in 1 for x and -1 for y. And we plugged in 2 for dy dx. So that should be right. 2 times 2 times 2 is 8, -8 minus 1. We should be right. That should be good. That should be the Taylor polynomial for f about x equals 1. And so now we have C. Second degree Taylor polynomial is used to approximate f of 1.1, given that the absolute value of the third derivative of x is less than or equal to 60 for all x, and 1 less than or equal to x less than or equal to 1.1. And so we're going to use that Taylor polynomial. This is going to be t of x, we're not going to call it f of x. It's not equal to f of x, and that would have given us a problem. Use Lagrange error bound to show that the approximation differs from f of 1.1 by at most 0.01. So we're going to find the next term in the Taylor polynomial. So that would be, we're going to look at the absolute value of third 1 times x minus 1 over 3 factorial, that's cubed, right? And this is going to be the maximum value in the interval. So this is going to be the max for f double prime of x. All right, been a while since I've looked at this, so if I get this Lagrange error bound wrong, I apologize, but this is what I recall. So this is going to be the error less than or equal to this. We want to go it's less than at most 0.01. So the third derivative, we got the maximum there. We said that's 60, right? Yes, that's 60. So this is going to be equals 60 absolute value times x minus 1 cubed. And this is at 1.1. So this is going to be 0.1 cubed over 6, which equals 10 times 0.001. 10 times that is 0.01. So I think we have shown that correctly. D. Now we're going to use Euler's method. Starting x equals 1, 2 steps of equal size to approximate f of 1.4. So we know, put the graph over here, this is at the point 1, -1. In Euler's method, we're going to use the tangent line approximation to go halfway. So we're going to 1.4. That means we're going to go to 1.2. We're going to go to 1.4. All right, so the tangent line at 1.1, we know that f of 1 is -1. And we know that dy dx or f prime of 1 is equal to 2. So So that means that the tangent line approximation is going to be y equals 2 times x minus 1. This would have been y plus 1, so this is going to be minus 1. And that's going to be the first approximation. So we're going to plug in 1.2 there. So that's going to give me 2 times 1.2 minus 1 is 0.2 minus 1. That's going to be 0.4 minus 1, which is negative 0.6. So that point is 1.2 negative 0.6 is our next point. And so now we're going to evaluate dy dx. Dy dx at that point what you see on there, which is going to be 3 minus 1.2 times y squared, which is negative 0.6 squared. 3 minus 1.2 is going to be 1.8. And negative 6 squared is going to be 0.36. 1.8 times 0.36. Go ahead and pick that. 48, 24, 28, 0, 36, 0.648. 0.648. That's our dy dx. So our approximation y equals, this is going to be, now we're going to have that slope starting at the approximated point, which is going to be 1.2 no, sorry, 1.4. Yes, we're looking at the line. We didn't do the line. Let's go do that. 2x minus 1 point. This is the point 2. And this is going to be plus negative 0.6. Negative 0.6 is going to equal 0.648. 1.4 is the next, so it's going to be 0.2 minus 0.6. And we're going to leave it there because we don't have to go any farther. So that means that f of 1.4 is approximately equal to 0.648 times 0.2 minus 0.6. Answer looks a little crazy, but hopefully we did it right. We'll check it later once we can see all of that, once we have time. Okay, that's number 5. That's our solution to number 5. So we'll do number 6 next.